Hello everyone, here we are going to present our theoretical research on stability and electronic and optical properties of ternary nitride phases of magnesium tin nitride. Our work also has been published on the Journal of Physics and Chemistry of Solids. Our work has been inspired by a recent synthesis of magnesium tin nitride in disordered Rocksalt crystal structure by a metathesis reaction under high pressure of 5.5 GPa at 850 degrees centigrade for 1 hour. Lattice constant and band gap has been reported. There is a possibility of some oxygen impurity in the material. In order to calculate various physical properties of the material, we have utilized WASP software that is based on density functional theory. GGS pseudopotential has been used in order to calculate structural and mechanical properties, whereas hybrid HSCO6 functional has been utilized to calculate optoelectronic properties. We have prepared magnesium tin nitride in disordered Rocksalt, disordered wurtzite, and orthorhombic crystal structures. We have also incorporated oxygen into the anionic sublattice in order to gauge oxygen contamination. The lattice constant for magnesium tin nitride in disordered Rocksalt crystal structure has been calculated to be 4.56 angstrom, which is closely matching with the experimental result of 4.48 angstrom. Similarly, its band gap also has been calculated to be 2.69 electron volt, that closely matches with the experimental result of 2.3 electron volt. We have also done formation energy analysis, where we have found that orthorhombic crystal structure has the lowest formation energy, that makes the other two crystal structures energetically metastable. Even though they are energetically metastable, we will see later that these two crystal structures are also mechanically and vibrationally stable. The value of effective masses for magnesium tin nitride in disordered Rocksalt crystal structure is the lowest among these three crystal structures, that makes it best for charge carrier transportation. As we discussed before, all the three crystal structures of magnesium tin nitride are mechanically stable. The Vickers hardness of the disordered Rocksalt crystal structure of magnesium tin nitride has the highest value among all three crystal structures. When we look at the absorption curve, we can see that absorption for disordered Rocksalt crystal structure starts at around 2.7 electron volt and it peaks at around 3.2 to 3.5 electron volt. Since there is not much substantial absorption for the other two crystal structures, we don't see any reflection in this visible range. When we look at the phonon situation, there is no any phonon population below 0 Hz. That means that all the three crystal structures are vibrationally stable. The phonon population for nitrogen can be found at a higher frequency range. The phonon population for magnesium can be found at an intermediate frequency range. The phonon population for tin can be found at a smaller frequency range. This helps us to conclude that the particle mass is inversely proportional to the vibrational frequency. Calculated electronic density of states closely match with the COHP analysis. When you look at the electronic population above the Fermi level, we can see that they are in the antibonding states. That helps us to conclude that electrons in the conduction band are loosely bound. When we look at the electron population for disordered Rocksalt crystal structure in between -2 and -5 electron volt, we can see that they are in some antibonding states. This helps us to conclude that disordered Rocksalt crystal structure has the highest formation energy among the three crystal structures. Finally, we can conclude that the calculated lattice constant and band gap for disordered Rocksalt crystal structure closely matches the experimental result. Magnesium tin nitride in disordered Rocksalt crystal structure can be utilized as absorber layer in the higher energy range of the visible range, whereas the other two crystal structures can be used as window layer in solar cells. Finally, we want to thank our funding agencies, National Science Foundation, University of Toledo, Air Force Research Laboratory, and Ohio Supercomputer Center. Thank you very much. If you have any questions, please contact me at my email address.